So the burning question in your heart may be, what happens when you have more than one stereogenic center? Well, you can have multiple stereoisomers. So for a molecule with n number of stereogenic centers, the max number of stereoisomers is 2 to the nth. Okay, so let's do an example. Let's say that you have 3 stereogenic centers. When you do this, what you're going to see is 2 raised to the third power, which will give you 8. Okay, and so with 3 stereogenic centers, there are going to be 8 stereoisomers that can be drawn. However, some of them can be the same molecule. So some of these stereoisomers will not be mirror images of each other, and those are called diastereomers. And these are just non-mirror image stereoisomers. So let's look at 2 examples. Let's say you have a problem that says find all the possible stereoisomers for 2,3-dibromopentane. Okay, and so when we think about 2,3-dibromopentane, the first thing you need to do is just draw it. And so we have 1, 2, 3, 4, 5, and then 1, 2. We've got a bromine here, 3, and we have a bromine here. Okay, then you need to identify the stereogenic centers. You have one stereogenic center here because you have 4 different groups. You have bromine, the CH3, this big group, and a hydrogen that's not shown. Then you have another stereogenic center there. You've got bromine, this ethyl group, and this large group here, and then a hydrogen that's not shown. Now, you need to draw this in a way that shows the 3-dimensional structure of the molecule to help you figure out your stereoisomers. So you need to redraw the stereoisomer and just arbitrarily arrange the substituents around the stereogenic center. And then you just need to draw the mirror image. So for example, if I were to come here, I'm going to say, all right, hey, look. I'm going to do the hydrogen here, the bromine here, the bromine here, and the hydrogen there. And so I'm going to call that A, okay? So that when we talk about it, we'll all be on the same page. And so now I need to draw the mirror image of that. And so when I draw the mirror image, that's what I get. And we're going to call that B, okay? After you draw the compound in its mirror image, you can place B directly on top of A and rotate B 180 degrees to see if those atoms align. So what do I kind of mean by this? I like to think of it as you just flip B like a pancake. Well, that was not helpful at all. Okay, you flip B like a pancake. And so we're going to flip B like a pancake. And when you flip B like a pancake, right, now this is right here. And then everything, and then it goes like this, and that goes up. Okay, so we've just flipped it over. And so now everything that was a dash is now a wedge. And so when we look at this, that means the hydrogen here is going to be on that solid wedge. The bromine is going to be on the dash. That hydrogen is going to be on the wedge. And that bromine is going to be on the dash. Okay, so this is B flipped. Okay. Now, we need to compare the flipped B here with A, okay, to see if those atoms align. So we have this group here, and we compare it to this group here. And on the wedge, we see we have a hydrogen and we have a bromine here. Then we look at this group here, look at this group here, there's the bromine, there's the hydrogen. So in this case, A and B do not align, okay? So A and B do not align. And that makes A and B non-superimposable mirror images. And so this means that A and B are enantiomers. Now, when we looked at this molecule, if we've got two stereogenic centers, that means you've got 2N, right, to give you the number of stereoisomers, max number of stereoisomers. All right, so that's the max number of stereoisomers. So we had 2, so 2 to the second equals 4. So A and B are the first two. So now we need to think about what are the other two, okay? So we need to draw another stereoisomer. So when we do this, so when I go to do this, the best way to do this is to look at this stereoisomer, the first one you drew, and switch to the groups on one of the two stereogenic centers, but leave the other groups the same, okay? So when we do this, right, I'm gonna switch these two, that's Br, and that's hydrogen, but now I'm gonna leave this one over here the same. And hydrogen here. So we're going to call this one C. And so when we call it C, okay, we can see that that's different than A, and we can see that it's different than B. What we need to do now is draw the mirror image. And so when we draw the mirror image, and let's call that D so we can refer to those really well. So now what we want to do is we want to flip it, right? So let's flip D. Right? Just like a pancake. And so when we do this, we have our structure like that. And then what we're going to see, I'm going to go ahead and draw my bonds. Okay, so we're gonna flip it here, and you should see where the H is on the wedge, and then the Br is back. And so again, kind of what we're looking at here is that H and we flip it, now it's poking out. I've got this BR, and now that BR is back, okay? And then the same thing, when we flip it, we find that now the BR is forward and this H is back, and those correspond to here and here, okay? And so now we need to compare with C to see the relationship. And so when we compare with C, we look here and we say, okay, look, this bromine's back. This hydrogen is forward, so that's not the same. Come over here, this hydrogen's forward, this bromine's back. That's not the same either. So that means that C and D are enantiomers of each other. So maybe the burning question in your heart is, that's great. What's the relationship between, for example, A and D? They're not enantiomers, but they're still sort of related. A and D are diastereomers, right? And then B and C are diastereomers. Right? We also see where A and C are diastereomers, and then B and D are diastereomers. So everything else, if it's not a specific enantiomer relationship, here are diastereomer relationships. Let's do another example. So in this example, we are looking at the stereoisomers possible for 2,3-dibromobutane, okay? And so we need to figure out how many we can have, and this has 2 stereogenic centers. So again, it's 2 to the second, 2 to the nth. And so we can have a max of 4, okay? To find the stereoisomers, we're going to arbitrarily form one stereoisomer. We're going to write it. And so I'm going to come here. And form that one. And I'm going to call that A. Okay. Then I'm going to draw the mirror image here. There. And we're going to call that B. Now, we need to then flip B like a pancake. So when we do that, we come here, here, and here. And then, right, we're looking at placement of this guy and this guy. And so we're going to come over here. And that means because we flip it, now the bromine is to the front and that hydrogen is to the back. And then here, that means the bromine's going to be to the back and the hydrogen's going to be on the front. And when we compare, right, we see that these are on different positions, so they're mirror images of each other. So for us, that means that A and B are enantiomers. And so now we have to draw another stereoisomer and evaluate it as well. And so we are going to switch the positions on H and Br, just like before, on one stereogenic center, but keep the other one the same. So we're going to come here. And okay, so A and B are diastereomers of C that are shown here, okay? And so now let's go and draw the mirror image of this. Sorry, I was on the wrong one. Right? And what we find here is that D is an identical molecule. So D is identical to C. I also want you to notice that there's a plane of symmetry right here in C, where it's the same on both sides. So we know then that that's not chiral, it's achiral. So C also has a plane of symmetry. And is achiral. Personally, I look for a plane of symmetry first. I just think it's easier to see, but everybody learns differently. Now, this is an example of a mesocompound. A mesocompound, right, is an achiral compound that contains tetrahedral, stereogenic centers, right? So C then is a mesocompound. And mesocompounds generally have that plane of symmetry, so they possess those two identical halves. So because that stereoisomer of 2,3-dibromobutane, C, is superimposable on its mirror image, this means that it only has 3 stereoisomers, right? So, and that also means that A and B are diastereomers of C, okay? So, this is something that you have to watch for. And again, really looking for that plane of symmetry is helpful. Now, maybe the burning question in your heart is, all right, Dr. Pierce, I have identified the stereogenic centers. I have figured out how many stereoisomers there are. I figured out which ones are enantiomers and which ones are diastereomers. But how do I name them? And I'm so glad you asked. So when we're talking about naming with stereogenic centers, you have to name each one individually. So when we look at, for example, this molecule, here, right? We know the name is 2,3-dibromopentane. But we need to tell the configuration of this center. And so we tell if this center is R and S independently of whether this center is R or S. So we need to, and I'm going to do one in red. We're going to come here and we're going to say, okay, look, that's 1, that's 4. This is going to be 2, and that's 3. And the lowest priority is on that dashed wedge, so I can just draw from 1 to 2. And so we can see there that that is S. So that's on the 2 carbon. So in the front here, you would go 2S and then comma. Then we're going to come here. We're going to say, okay, that's 1, that's 4. 2 is here, and 3 is here. So we're going to draw that way, like we turn a car, that's R. So that's going to be 3R, and we end, and then we do a dash there. So this would be 2S, 3R, 2, 3, dibromopentane. Now, identical compounds have the same RNS designations at every tetrahedral stereogenic center. Okay. Enantiomers have the exact opposite RNS designations. Right? And then diastereomers, right, have the same RNS designation for one stereocenter, at least one stereocenter. And opposite for at least another. Okay, so let's look at acyclic compounds. So we have cis-1,3-dibromocyclopentane, and we've got two stereogenic centers here. And so it can also have a 2 to the nth, which would be 2 squared equals 4 max stereoisomers. Now, we've seen we can have cis, and trans stereoisomers. And so these are stereoisomers, but not mirror images. So we refer to these as diastereomers. Okay. Now, to find the other two stereoisomers, if they exist, we draw the mirror image of each compound and determine whether the compound and its mirror image are superimposable. So, for example, if we have the cis isomer here and we draw the mirror image, that's identical to the original, right? So the cis isomer, right, is superimposable on its mirror image. And there's also, if you look here, a plane of symmetry. So that means A is an achiral meso compound. If you come over here and then look at B, and we draw that mirror image, right? The trans isomer there is non-superimposable, and so that makes B, and let's call this C, different compounds. So B and C are enantiomers. Right? So because one of the stereoisomers of 1,3-dibromocyclopentane is superimposable on its mirror image, similar to the previous example, we're only going to have 3 stereoisomers. So that's why we say that there's 4 as a max. So this ends our discussion of identifying stereoisomers and stereogenic centers and naming them. In the next screencast, we're going to talk about some properties of isomers. So I feel like it's really fitting to end on a summary of everything that we've learned. So isomers are different compounds with the same molecular formula, and you can have constitutional isomers right? And these are isomers having atoms bonded to different atoms. So we can have different functional groups. And then you can have stereoisomers. These are isomers with a difference in 3D arrangement only. When we come here, these constitutional isomers are going to have very different names. And so my suggestion is always, to count your atoms, and you can name them, and if they have two different names, then they're going to end up being constitutional isomers, as long as they have the same number of atoms, right? So like 5 carbons and 14 hydrogens or whatever. Then back over here to stereoisomers, we're just talking about 3D arrangement. So these are going to have the same functional group. And then you can have enantiomers, which are mirror images, or diastereomers, which are not mirror images, but still related. Here is a way to help you determine the relationship between the molecule. If you have two non-identical molecules, the first thing you need to ask yourself is, do they have the same molecular formula? And if the answer is no, they are not isomers. If it is yes, they are isomers. Then ask yourself, are the molecules named the same except for prefixes like cis, trans, R, and S? If the answer is no, they're constitutional isomers. Naming can really help you identify constitutional isomers, and that's my suggestion at this step. If you know they're isomers, name them. If the answer is yes, then they are stereoisomers, and you need to determine if they're mirror images of each other and whether they're enantiomers or diastereomers. If you have any questions, please feel free to stop by my office. I am happy to help.